My name is Shane Skinner, and for this presentation we will be covering VeSys design and harness. First, I'd like to take a minute to consider a scenario. Let's say you're an engineer responsible for working on one of the harness designs in this truck, and after months of hard work it goes into production and it's now on the road. Now let's say a few months later they are all then recalled because of an issue that can be traced back to the harness design you were responsible for. This is obviously a terrible situation for the individual engineers responsible, but also terrible for the company as a whole when you take into account the financial repercussions, time it will take to resolve the issue, and damage to brand image. This is essentially the worst case scenario that highlights the importance of getting your design correct the first time. Unfortunately, this is one of the potential side effects of a common industry trend. Electrical content is always increasing regardless of the industry and application. This increases the cost to do the initial design as well as manufacture the harness, increases the overall design time due to complexity, and similarly, every time something new is added to a design, the chance of inducing an error comes along with it. With our tools, we attempt to address these issues through the use of automation, collaboration, and verification. The overall goal is to reduce your design costs, design cycles, and risk to avoid the types of disaster scenarios like the one that was just highlighted. For this presentation, we will be working with a small tractor design. The wiring and harness designs are partially complete, so the first step will be to finish off the wiring design. Next, we will perform analysis to verify the changes we made. Then we will synchronize our wiring and harness designs and perform some detailing on the harness. Then finally, we will utilize automation to select the appropriate parts for our harness and generate a couple of reports. We will start by updating the wiring design. First, we'll update the style set. Then we'll add the circuitry and connectors for brake lights. We will also add a multi-core and overbraid to our instrumentation diagram. Here in our lighting diagram for our tractor design, we need to update it with some brake lights. Before we get to that though, we'll also update the style set, as the current color scheme is a little on the distracting side. We can do that via the style sets dialog, and that will allow us to update the look and feel of our diagrams without changing any connectivity or needing to recreate anything. First, we'll disable the names for our wires as they're currently just cluttering up the diagram. And we'll also set the color of our wires back to the default. We'll make our devices black. And we'll set our connectors to a light purple color. Once we're satisfied with our selections, we can go ahead and apply the style across the design all in one go and make things a little easier on the eyes. And now we need to actually create the circuitry for our brake lights. Since it's similar to the circuitry that already exists for our other lights, we'll go ahead and reuse it. And by copying that, we bring over the library part assignment as well as any properties that might have been assigned to help save us a little time. And now all we need to do is add an additional switch, as our brake lights are independent of the light select. Next, we'll want to rename our devices and connectors to give them more meaningful names. We'll start with a resistor and call it R5. We'll also update its value, which comes into play when running analysis. For our switch, we'll call it brake light switch. And we'll also assign a library part. By doing this, we can utilize some automation to generate the appropriate harness connectors for this device. So with that library part assigned, we can then use the generate harness connectors action to automatically create the appropriate connectors. If we go back and look at the library part assignment really quickly, we can see that there's an additional part number assigned for its connectors. By running the generate harness connectors action, not only do the connectors get generated on the diagram, but the appropriate library part gets assigned automatically to help cut down on human error and speed up the process of creating the connectors. While we're at it, we'll also rename the connector so it's a little easier to work with once we pass it over to the harness. And then we'll update the names for our left and right brake lights as well as their connectors. Next, we'll add a note to describe the behavior of our light select switch. For position 1 of the switch, we'll say all of our lights should be powered off. For position 2, only our warning lights should be powered. For position 3, our warning lights and front lights should be powered. And for position 4, our front lights and middle lights should be powered. And position 5 won't be used. We can then associate the relevant objects to this note so it's easier to locate in the design. So we'll select the lights controlled by the light select switch, the light select switch itself, and the diagram that the circuitry is part of. Next, we'll make one final update. We'll add some multi-core and overbraid to our instrumentation diagram. You can do that via the quick add actions, which use a default multi-core and overbraid definition to simplify adding them to the design. And now we'll go ahead and pass this off to our team member to perform analysis and verify the design is working as intended. In this portion of the demo, we touched on a few of the features that help boost your productivity. Style sets enable you to quickly update the graphical representation of your diagrams to meet corporate or customer standards. Generate harness connectors makes connector assignment significantly faster and less error-prone by utilizing your parts library. And quick add actions simplify multi-core and overbraid creation. Now that the wiring design has been updated, we need to perform analysis to verify the lighting circuit is behaving as intended. We will assume the role of a team member rather than the original designer to utilize some of the collaboration functionality as well. First, we will use qualitative analysis to find any connectivity issues, then record the issues via comments for the original designer to correct. Then we will perform numerical analysis and correct any additional issues we find. Back in the lighting diagram, the first thing we'll do is open the note the designer left us to review the behavior we're looking to verify. For our light select switch, position 1 should have all of our lights powered off. Position 2 should have only our warning lights powered. Position 3, our warning lights and front lights should be powered. And for position 4, our front lights and middle lights should be powered. In this case, position 5 on the switch isn't used. We can use the associated objects list to cross-probe and verify that this note applies to the circuitry we're interested in. Once we've confirmed that, we can start analysis via the Analysis tab. The color of the diagram will update to highlight any issues with the design, as well as the flow of current. In this case, it's cyan to tell us that there is no current flow in this particular diagram. And since both of our switches are in the open position and there's no path to ground, that's to be expected. We can control the switch position via the Analysis tab as well. First, we will try closing the brake light switch. It appears like we are not getting any power still. And if we cycle through the light select positions, looks like our devices are still failing to receive any power. So this could obviously indicate an issue with the design, but to be sure we'll have to trace connectivity back to its origin. Here we have a cross-reference indicating this particular wire is coming from our power distribution diagram. We can use that to quickly jump over to the diagram of interest. And here we can see we do in fact have power in our design, as indicated by the green color, with the arrows showing the direction of the current flow. So it appears that we're losing connectivity at the ignition switch. In addition to controlling your switches via the Analysis tab, you can also do so via hovering over them. Here it looks like our ignition switch is set to position 1, or open, so that would explain why we aren't getting any power to our lighting diagram. If we close the switch, Analysis will update in real time in the background to show us the changes in our design. And here we can see that the current is now flowing to our lighting diagram. And if we come back to the lighting diagram, we can then trace that all the way down through our brake lights. Now that we've confirmed our diagram is capable of receiving power, we can continue with analysis. Position 1 should have all of our lights powered off, which is the case, as indicated by the cyan color. Position 2 should have only our warning lights powered, which is the case, as it's green. And for position 3, it looks like we have our first issue. Our warning lights are not receiving any power. Position 4 also appears to have an issue. Our warning lights are receiving power when our front lights should be instead. And for completeness, we'll verify if position 5 isn't doing anything, which it isn't, so that's good. Let's take a closer look at positions 3 and 4 to see if we can figure out what the issue might be. For position 3A of our switch, goes to wire 253 and our front lights. And for position 3B, it goes to wire 250 and also to our front lights. It appears that the problem in this case is there's currently no connection to our warning lights, so this particular state can't be satisfied. For position 4, 4B goes to wire 255 and our middle lights, which is fine as those need to be powered in this case. And position 4A goes to wire 251 and up to our warning lights. So it looks like that particular wire should actually be going to our front lights. So the overall situation we have then is 2 wires going to our front lights, one of which should be going to our warning lights, and a wire going to our warning lights that should be going to our front lights. So the fix in this case would be to swap a couple of wires. I'm going to select these 2 wires here and then leave a comment for our design engineer to let them know what needs to be updated. Then at this point, we will reassume the role of the design engineer and say this is the comment we get back from our team member. We can use it to quickly find the issue in the design and then refer to the actual comment to understand what needs to be changed. So here we have to swap a couple wires. So we'll use the Manage Connections dialog to do that. We have pins 2 and 3 going to wires 253 and 251. And we'll quickly swap those 2 wires. And now that we've done that, we'll leave a reply to the comment indicating we've resolved the issue. And that will create a thread that can then be referred to for future reference. Now that that's been fixed, we'll return to doing our analysis. So position 3 should have our warning lights and front lights powered, which appears to be the case now. And position 4 looks like we have our front lights and middle lights correctly powered. So at this point, we've finished performing analysis to verify our connectivity. We'll go ahead and switch over to Numeric Analysis. And Numeric Analysis takes into account wire cross-sectional area and resistance, so it provides an additional level of detail that qualitative doesn't. So for example, if we hover over an object with Numeric Analysis running, we'll get a pop-up with the additional information. So in the case of this wire, we can see it's rated at maximum current values, the current voltage, resistance on the wire at this point in time, etc. And what you see here is dependent on the analysis model associated with the object. So for example, if we take a look at our lights, they have a lit condition defined in their analysis model. So not only can we determine if they're receiving power, but if they're receiving enough power to function properly. So for the remainder of this numeric analysis, we'll be looking for that lit condition to be set to yes. For position 2, it appears that the lit condition is met for our warning lights as well as our brake lights. And for position 3, it appears that the lights are not receiving enough power, as that lit condition is set to no. If we take a look at our analysis output window, we can see that we've actually blown a fuse. If we jump back to our power distribution diagram, you can see fuse F3 has changed color to indicate it's failed. If we hover over that, well, you can see that a 10 amp fuse is currently assigned. So in this situation, we'll say that we know all three of these fuses are supposed to be 30 amp fuses. So this is just a situation where the wrong part number was assigned to this particular device. So we can fix that really easily. The part selection dialog will filter based on the context from where it's invoked. So since we invoked it from a device with the fuse symbol assigned and 2 pins, it will only show us parts in our library that meet those criteria, so we're not sifting through every single part in our library. So go ahead and select the 30 amp fuse and swap that out. Now we'll see that the blown fuse warning has disappeared and the color of the fuse is updated to indicate things are okay. Now we'll return to the lighting diagram, and we can see now that the lit condition is being met for all of our lights. And finally, we will switch over to position 4. And it appears that all of our lights are illuminating in this case as well. But we do have a potential issue with one of our wires. This magenta color doesn't necessarily indicate a failure, but what it does tell us is that the current on that particular wire is over its rated value and approaching its maximum. So in this case, we'll go ahead and play it safe and up the wire spec to handle the current. Now we can see the current is well within the rated value. So at this point, we've finished our analysis of the lighting diagram, and we're ready to pass our changes off to the harness via synchronization. In this portion of the demo, we demonstrated how analysis can be used to achieve better insight into a circuit's behavior. Analysis also enables you to find and fix issues early in the design process and avoid propagating design errors downstream, where they become more difficult to detect and significantly more costly to correct. We also highlighted some of the collaboration functionality via comments and notes, which is valuable in supporting team-based design environments. They allow you to document important design information within the tool itself, so it's easier to keep track of, and enables you to utilize the information interactively via cross-probing to make communication clearer. To propagate the changes we made in our wiring design to the harness design, we will need to synchronize the two. First, we will update some of the attributes for the new content we added to prepare for synchronization. Then we will move the newly added content to the correct location on the harness and make a minor change to the topology. And finally, we will update our tables to display additional information. First, we'll open up our harness design. Here we can see that a majority of our connectors have already been placed, coming from a previous synchronization run. But now we will need to synchronize again to bring in the changes we made to our wiring design. Notice the name of the harness is primary harness, which will come into play in the next step. So there's one more thing that we need to do before performing synchronization. We need to assign the harness attribute. If we look at the brake lights, we can see that they already have the harness attribute set with the value of primary harness. And that's because we copied them from the middle lights, which were already part of the harness. So we'll need to add this attribute to the content that we added outside of the copy and paste. We'll start by adding it to the wires, and then to the brake light switch connector and brake light switch itself. Now at this point, we are ready to synchronize. Upon completing synchronization, we'll see that we now have a couple of connectors added for our brake lights, as well as the brake light switch, and also a couple of splices. So the next step will be to add these to the appropriate location on the harness. We can do that simply by moving them. And at this point, we may also want to manipulate the actual topology of the harness. We can do that very quickly by simply hovering over a particular bundle and then using the grab handles. So we'll go ahead and add a bend to our brake light bundles, and also move them a little bit farther away from the main harness. We'll do that for the other side as well. Then if we apply styling, we can get the connectors to automatically reorient for us. And next we'll take a look at the tables in our design. In the top right here we have a from-to wire connectivity table that automatically updates as we perform synchronization. So here we can see the connectors for our brake lights, the switch, the splices, and even the multi-core have all been added after performing synchronization. Over on the top left of our diagram, we have a table listing all of the connectors contained in our harness design. And then we have the individual wire tables for each connector as well. And all of the tables are completely configurable in terms of what they show and how they appear, and that's all controlled via styling. So for instance, we'll add some additional columns to our wire tables. We'll turn on wire part numbers as well as terminal part numbers. Upon applying styling, we can see the table gets updated, and then applying styling to the whole diagram will update all of our tables at once. And then it's just a matter of reorienting the tables and text to meet your needs. And that wraps up synchronization. So now we're ready to select the appropriate part numbers for our harness and also generate a report. In this portion of the demo, we showed how simple it is to pass changes between your wiring and harness designs to ensure they're always in sync with each other. We also highlighted bundle manipulation via grab handles and table customization via styling, both of which help keep your designs clean and concise and give you full control over how your harness designs are presented. Now that we have successfully imported our changes from the wiring design, we can select the appropriate wire and cavity component part numbers for our harness design and calculate wire lengths. We will do this via automation and the library definition. Then we will wrap up by generating a bill of materials report and creating our own custom report. Before we start generating reports for our harness design, we'll have to select the appropriate part numbers for our wires and cavity components. This is a very quick and easy process with automation. We can use part select that pulls from our library definition to select the appropriate part numbers for all of the wires in our harness design. And one more thing that we can do for the sake of reporting is calculate our wire lengths. You can also use automation to select the appropriate cavity component part numbers for our connectors. We can use cavity component management to select the appropriate parts on a case-by-case basis for each connector. Or we can also use part select in this case to select all of them at once for every connector in the design. With our library parts assigned, we can go ahead and start generating reports. We'll go ahead and use the pre-configured bill of materials report first. And this simply pulls from all of the data that's already in our design with with no need to organize it or pull it together ourselves. And we can save these reports in the HTML format or print them for future reference. And in addition to using the pre-configured reports, it's also very easy to create our own custom reports as needed. So for this example, we'll go ahead and create a simple from-to report for our wires. So we can start by adding the name of the wires to the first column. We'll include the part number assigned to each wire in the second column. And then we will use the remaining two columns for the from-to list. Then we'll go ahead and rename it to from-to. And then these custom reports can be saved and reused for future designs. Then once a custom report has been saved, you can find it in the list along with the pre-configured reports. In this portion of the demo, we showed how automation can be used to streamline part selection, saving additional time and further reducing the risk of error. We also demonstrated how simple it is to generate reports and customize them to meet your company's needs. And with that, we wrap up the presentation. VeSys provides functionality that helps engineers deliver rapid, right first time, error-free electrical and harness designs. Through automation, analysis, and a plethora of time-saving features, it allows design teams to put their effort where it counts. Innovation. Thank you.